Hello and welcome back. This is presentation 6.4. The topic is the central limit theorem, the foundation of statistics, and this material is in your workbook chapter 6 and your textbook chapter 6. So let's begin. We begin with the statement of the central limit theorem. As you can see on the screen, we'll start with a random variable x that's normally distributed with mean 70 and standard deviation 8. We're putting in here the various details. We can be 95% confident that x's will fall between these intervals 70 plus or minus 1.6 times 8. That is to say, plus or minus 15.7 of the mean between 54.3 and 85.7. And now we begin to take random samples of size 25. Here are 4 such random samples. And you'll notice that they're all around, they cluster on 70. And the distribution, if we collect several hundred of these, they'll follow a distribution like you see here. And the population mean, mu sub x bar, they'll cluster around this mu sub x of 70. And the mean of the x bars, the mean of all these red x bars, will be approximately equal to 70, the same as the population. However, the standard deviation is sigma over square root of n, and sigma is 8, n is 25. This turns out to be 1.6, and this gives an idea of how these cluster, these x bars cluster about these population mean. As the sample size increases, this sigma sub x bar will get smaller and smaller, eventually going to 0. Now we're going to look at sample sizes of n equal 25. And here we've generated 100 random samples of size n equal 25. And you can see here the sample means. There's 100 of these going across. The mean of those x bars is 70.12. And the standard deviation is 2.08. That's the standard deviation in those sample means. Now looking at the distribution of x bars, we're saying these x bars here, these sample means, will cluster around 70, and the standard deviation will be 10 over square root 25, or 2 in this case, giving rise to this notion of an error plus or minus 3.92 with 95% confidence. Those values are seen on the screen there, and you should work them out. This is called a confidence interval for x bar. Now we're going to look at the distribution of x bars based on n equal to 100, and you can see here that the x bars, see how close, how much they cluster around 70? Very, very close. The mean of these x bars is 70.09, and the standard deviation of the x bars is 1.01. And we're going to look at the distribution of x bars that you see coming on the screen here now. We're saying those sample means that you see will cluster around 70. The standard deviation now is 10 over square root of 100, or 1. And compare this with 1.01 here, very, very close. This is the theoretical value. And we're going to look at a confidence interval, 70 plus or minus 1.96 of those standard deviations in x bars. And this gives rise to, this is called the error term, gives rise to this interval. And you can see here now that this is called the confidence interval for x bar. That is to say, for sample size of 100, you can be 95% confident you're within approximately 2 units of the population mean. Now we're going to look at the box plots for the various categories, and you can see here for the population of individual x values, we see here the box plot on the left. But however, for sample size n equal 9, this means that for sample size of 9, the means will cluster in this range. For 25, they'll cluster in this range, n equal to 100 here, and this is 1,000 over here. And suggesting that as n increases, these box plots will get smaller and smaller, eventually going to 0. As n increases, sigma sub x bar, which is variability, will get closer to 0. And when n becomes the population size, then this sigma sub x bar will be 0 because there's no variation in the x bars. Here we're going to apply this. We have the SAT scores, Strategic Admissions Test, mean at 1518, standard deviation 325. If one SAT score is randomly selected, we're going to look at the population here between 1550 and 1575. The Z score is 0.098. On the right, 0.175. Going to the table, we can see here that the values between these two blue arrows, it turns out to be 0.5391. For the other case, 0.175 is halfway between these two values, and that is 0.5695. And the area is the difference between these two numbers here, and you see them coming on the screen, 3.1%. And that's the answer. We're going to look at a random sample of 25 SAT scores. And here's where we apply the central limit theorem. We're saying the mean of the x bar should be around 1518, but sigma sub x bar will be sigma over square root 25. Turns out to be 65. Now we're going to look at the same intervals, but we're going to divide by 65, which is your sigma sub x bar now, since we're talking about x bars. The Z score on the left here is 0.492, on the right 0.877. Going to the table, you can see here the value between these blue arrows is 6886, which represents the area up here, and the other one is 0.877, and that number is 0.8098. Check your table, and of course the probability of the x bar be between 1550 and 1575 is the difference between these two values, or 12.1%. And that's the end of presentation 6.4. We ask that you review this on your own and go to presentation 6.5.